Hi, I'm Site Bai from Purdue University, Department of Computer Science, and I'm presenting our ICLR 2024 paper on local composite saddle point optimization. This is joint work with my advisor, Professor Brian Bullins. Saddle point optimization is when the objective involves two variables, and we want to minimize with respect to one variable and maximize over the other. The applications include training gangs, multi-agent reinforcement learning, matrix games, etc. Algorithms for finding the saddle point include mirror prox and dual extrapolation. They are known as extra step methods that carry out a two-step evaluation of a proximal operator, which involves a Bregman divergence Vx associated with a distance generating function h. As the data size grows larger, the scale of these problems require distributed optimization, where our central server coordinates collaborative learning among clients. Federated learning, in particular federated averaging, also called local SGD, has been proposed that leverages local updates to improve communication efficiency. In each round, clients learn a synchronized global model locally through multiple local updates, then send the model to the server to produce a new global model through averaging. This mechanism has been applied to saddle point optimization, where the objective would be an average of local functions. In many machine learning problems, however, non-smooth regularizers are added to impose specific structures on the solution. Examples include L1 regularization for sparsity, nuclear norm for a solution with low rank, and an indicator function to impose constraints. We noticed that none of existing distributed algorithms for saddle point problems can solve composite objectives or those with constraints. Meanwhile, Yuan et al. Have identified the curse of primal averaging in federated composite optimization. That is, specific regularization imposed structure on the clients may no longer hold after direct averaging on the server. For example, each client obtains a sparse solution, yet averaging the solutions across clients yields a dense solution. As a result, they propose federated dual averaging that aggregates the solutions in the dual space before projection to the primal space. Unfortunately, dual averaging is not the ideal method for saddle point optimization, as even in the deterministic case, their convergence rate is 1 over square root t, whereas extra step methods converges at the rate of 1 over t, which is known to be optimal. Therefore, we propose federated dual extrapolation, abbreviated as FedDualX, which is, to our knowledge, the first algorithm for saddle point optimization with non-smooth regularization under a distributed paradigm. We first derive its convergence rate in both distributed and sequential settings, then demonstrate experimentally its effectiveness on various composite saddle point tasks. To adapt to composite regularization, we propose the notion of generalized Bregman divergence for saddle functions, which merges the regularization term into its distance generating function. Correspondingly, we also update the proximal operator. With these novel technical accommodations, we present the FedDualX algorithm. The highlighted part carries out the two-step evaluation of the generalized proximal operator on each client, which resembles the classic dual extrapolation updates. And the averaging is done with dual client variables to impose structure on the aggregated variable on the server. With some standard assumptions, we derive the convergence rate of FedDualX with respect to R, the communication rounds, K, the local update steps, and M, the number of machines in terms of expected duality gap. In addition, applying FedDualX to distributed composite convex optimization, the convergence rate matches that of federated dual averaging. The sequential version of FedDualX, namely composite dual extrapolation, has a matching rate to stochastic extra gradient descent and to composite mirror prox in the deterministic setting. We first apply FedDualX to composite bilinear problems, including L1 regularization with L infinity constraint and nuclear norm regularization with spectral norm constraint. We see from the duality gap that extra step methods, including FedDualX, converges faster than federated dual averaging. In terms of inducing structures, we see that with dual space averaging, the solution generated by FedDualX is more sparse or has lower rank than federated mirror prox. Next, we apply FedDualX on the universal adversarial training of logistic regression, with sparsity regularization on the attack. We see from the loss curves that Fedule X converges faster than projected gradient descent ascent, which is the Euclidean version of mirror descent. Also, the attack generated by Fedule X is more sparse as visualized on the right. Thank you for watching.